Okay, so let's take a real quick look at what happens when we take limits as x approaches infinity. So in this case, we're really looking to see what's kind of the end behavior of these once you go really far one way or the other in on the x direction. So we write this. So let's take a quick look at an example. Uh, Let me think of one. How about Oh, here we go. I got an idea. How about let's do sine x over x. All right. That's probably a good place to start. So when we do these, a lot of times we're looking for convergence. If it converges on one, or if there's a vertical asymptote, which it'll get close to. So this isn't a graph of sine x over x. This is just kind of for example here. Let's say you have some kind of a graph, and let's say this is going to be, let's say you have a horizontal asymptote at like let's say 2. And so here we go, and you have some graph that maybe it'll shoot up like this, and it'll get closer and closer and closer to 2 the further that you get out, but it's never going to cross 2. So it'll converge on 2, and that's kind of what we're looking at oftentimes. Now these can be like infinity also, or oftentimes they won't converge to anything. So but like in this case, so let's take a look at our sine x over x example here. So I'm going to pull up so let's say you have something, this one is kind of, I like this one because it just sort of looks neat. All right, so and here's maybe, while as long as we're here, let's sort of look at why we need to do this, why we need to look at end behavior, because really with graphs it's all about what domain and range you're looking at. So let's say that you are looking at just this part of the graph, right here. You could say like, oh well, apparently it converges here, or there, but really we have to figure it out more mathematically to see, or to kind of broaden out our scope. So as you can see here, if you zoom out, this is going to go down and up and down and up and down and up. And it's going to go right, if we zoom out, it's going to get smaller and smaller and smaller and smaller till eventually it's going to stop. Because, and we can think of it kind of logically, you think as x gets bigger and bigger and bigger, then that means that these little oscillations here around x are going to get smaller and smaller and smaller, because that fraction is going to have a bigger denominator. So naturally, if you kind of look at it logically, you could say, well, more often than not, or not more often than not, but this seems logical that this is going to converge to 0, because when x gets really, really big, then again those oscillations are just going to get smaller and smaller and smaller around 0. This is actually kind of neat as long as we've got this up. We talked a little bit earlier about the squeeze theorem, and how you can kind of, it's useful for proving things and stuff. Well, this is actually one instance where the squeeze theorem, oops, there we go, where the squeeze theorem can come in handy. So let's say, okay, let's use, so check this out, 1 over x. All right, and then let's do negative 1 over x. Ooh, looks cool, huh? Okay, I think it looks kind of neat. All right, so let's zoom in here. So you'll see here, this graph right here, the gray graph, is the value of 1 over x. And if you'll notice here, the function of sine x over x doesn't ever, it can equal it, like it'll equal it there and there, but our function will never get any bigger than 1 over x. So we know from kind of from previous lessons and just from intuition that as x gets close to infinity, it's going to approach 0. And so the same thing with 1 over negative x. So in this case, we can say, well, the sine x over x is kind of complicated, but we know that this always has to lie between either 1 over x or 1 over negative x, or negative 1 over x, right? So because we know that, I know that 1 over x and negative 1 over x converges to 0. And since this will never be bigger than any of these, by the squeeze theorem, we know that this is going to converge to 0 also. So that's kind of a neat little thing with the squeeze theorem. So that's I guess you could call it a practical application of it, because sine x over x might not be as intuitive. So you say, well, how are you sure that it converges to 0? Well, we have since the limit as x approaches infinity of 1 over x equals 0, and limit as x approaches infinity of negative 1 over x, running out of room, equals 0. Therefore, by the squeeze theorem, limit as x approaches infinity of sine x over x equals 0. So, that's, I don't know, that's not really in there, but sort of bonus material. So that's a really practical, good illustration of how we can use the squeeze theorem. But okay, so let's go back to our graph. Now, let's say you get something real crazy, right? Whoops, that's delete. Okay, let's say, all right, I'll make 2x up to the third plus 5 divided by, let's do something squared, 3x squared. Let's do plus 1. All right, so let's say you have a graph like this, and you say, well, really, okay, you can kind of inspect this graphically and say, oh, that's kind of cool looking, I guess. But how do you know that if you zoom, it looks like it goes out to infinity, so it looks like it doesn't converge on anything. But how do you know for sure that it does? Like maybe if you zoomed way out, this would turn down, and then it'll kind of turn up and converge on somewhere. So what this chapter goes over is a couple of techniques that you can use so that we really can be sure of what the end behavior is. So let's just take a quick look at that. These are especially with polynomials, with rational polynomials, and it's kind of a cool trick. So the equation we used y equals 2x cubed plus 5 over 3x squared plus 1. Okay, so if I'm looking at this, well, we're going to take the limit of this. So let's do the limit as x approaches infinity. There we go. This will be a little bit better. 2x cubed plus 5 over 3x squared plus 1. So here's the technique that you can learn is you take the highest order of the polynomial. So looking at this, say, okay, this one is squared, so this one is 2, and this one up here is cubed, so that's 3. So this is going to be the highest order of the polynomial. So we're going to divide everything by whatever that is. So in this case, we're going to have 2x cubed over x cubed plus 5 over x cubed divided by 3x squared over x cubed plus 1 over x cubed. All right, and so we're still taking the limit. So we're taking the limit as x approaches infinity. So looking at this, okay, now you gotta have to sort of think of it logically. All right, so the x cubed and the x cubed are going to cancel out, so I'm left with just a 2. Plus, All right, so I've got 5 over some really massively huge number, right? Well, 5 over anything infinity is going to be 0. It's going to approach 0. So 5 over x cubed we can just call 0. Now down here, I've got 3x squared over x cubed. So let's simplify that a little bit. So we can come down here. This is going to give me 3, actually just 3 over x, nothing else on the top. All right, so if this simplifies to 3 over x, when x gets really, really, really big, this is going to approach 0 also, right? So we're going to have a 0 down here, because 3 over some really huge number is just 0. And then the same thing with this one, 1 over some really, really big number, that's going to be 0 as well. All right, so we've got 2 over 0. So that's, you know, you never want to divide by 0 in math. That's always kind of a bad thing. So in this case, we know that this limit does, is in fact, infinity, because anytime you have 0 in that denominator, how many times does 0 go into 2? Well, 0 goes into 2 an infinite amount of times. So looking back at our graph, we know that this is just going to keep going up and up and up forever and ever and ever, and it's not going to turn down. So let's go over one more example and see if this works. If I can move this, I'm kind of reaching the bottom of the page here. All right, let's go over one more example, one that doesn't go to infinity. So let's say we have the limit as x approaches infinity of 2x to the, we'll do to the 4th, minus 3x cubed over x to the 4th minus 2x squared. So now we're going to use the same technique. We're going to say, okay, well, I'm going to divide by the highest order of the polynomial. Well, these are both x to the 4th, so I'm going to divide everything by x to the 4th. X to the 4th minus 3x cubed, x to the 4th over x to the 4th minus 2x squared. Okay, so let's simplify this. On the top, I'm going to have 2, because these x to the 4ths just cancel out, minus 3 over x. That cancels, and all but one of those cancels, over 1 minus 2 over x squared. Okay, so I'm taking the limit as this approaches infinity. So because I'm doing that, 2 just stays the same. 3 over some really huge number is just going to equal 0. We've got 1 on the bottom minus 2 over some really huge number squared. Well, that's just going to approach 0 also. All right, so this leaves me with 2 over 1. So I know that the limit here, as this gets really, really big, is going to approach 2. So let's just take a real quick look at this graphically, just for fun, to see kind of what it looks like. So I've got on the top 2x to the 4th minus 3x cubed divided by x to the 4th minus 2x squared. Alright, so clicking on this and zooming out, there's 2 right there. And as you can see, this does, in fact, at least graphically, ooh, it's kind of a funky little dip there and a little whoop. Alright, but this does, so regardless of that, it looks like 2 is going to be where it converges. And so it's never going to pass 2. And we can be sure of that because of the calculation that we did right here.